Hi everyone. Maybe am I audible, right? So like we'll start within 2 3 minutes. So we'll start with today's session. So this is week 4 of problem solving sessions of the course titled as Sensor Technologies, Physics, Fabrication and Circuits. My name is Shomrat Bhattacharjee. Here is some brief information about me. I am a PhD student in the Department of Electrical Engineering, IIT Jodhpur. My research interest lies around the domain of neuromorphic computing with flexible and organic transistors. I have completed my bachelor's degree in physics from Calcutta University. After that, I have completed my master's in electronics. More details can be found from this site, which is my site. And like if you want to connect with me, here is my social media handle. Every week we like I take a class at from 7 to 9 every Monday. So moving on to this is the basic course layout. This is a 8-week course, and up until now we have completed this like parts where I have like discussed about the basics of sensors, the basic introduction and so things, and then we are moved towards the parameters, the key parameters to characterize a sensor is good or is usable in our like use case or not. Then we have learned about the physics of the sensors, where we have learned about the capacitive sensors more in depth, and then we have started the basic theory of the thermal sensor and so things. Now in this week we'll learn about the thermal sensors more in depth. Along with that, we'll learn about the chemical sensors, the electrochemical sensors. Along with that, we'll learn about the impedimentatic sensors. So this is the basic layout of this week's class. That is the basics of the thermal sensors, and then we'll move towards the chemical sensors, electrochemical sensors, and more chemistry-based sensors. And then we'll learn about the impedimentatic sensors, and we'll end with some like few questions and like problems. So let's start with this. So last week actually what happened that I was unable to complete the question. So we'll start with that, and then we'll move towards the like main topic for today's class. So last week I have given you guys a question. A coaxial capacitive sensor is immersed in a container of height 100 centimeter. So the height was given as 100 centimeter. The ratio of outer to inner radius, that is RB by RA, was given as 2. When a constant DC source of 10 volt is applied as shown in the figure from this side to this side, and a constant current of 6.5 nanoampere flows through the external circuit. So we need to find the speed with which the water level is rising. We need to know the speed of rising of the water level in this coaxial container, you can say. So and also there was an assumption where the external circuit has zero resistance. So how we have solved this in the previous class? Sorry. Yeah. So how we have solved it? So at first we know that C is equals to 2 pi epsilon divided by ln of RB by RA. So from this we have got like in the previous class we have already discussed about it. Here the epsilon was 80 into epsilon naught, which was nothing but 80 into 8.854 into 10 to the power minus 12 meter cube kg inverse is square. So this was the value like we have got from this equation, and what we have done that we have the value of charge, which is nothing but CV. So charge is like sorry, not the charge. The current is the change of charge with respect to time. So what we have done in this case was dV dt plus V of dC dt. Here as the applied voltage was voltage is of DC DC voltage, so that's why this term will become 0. So eventually I equals to V into dc dt. Now we know the value of I here. From here we know the value of I, that is 6.5 nanoamperes. So what we'll do, we'll put everything in the equation. So this will be 10 volt DC into DC dt equals to 6.5 nanoampere. So the value which we have calculated was, we have determined the value was nothing but 6.5 into 10 to the minus 1, that is 0.65 nanofarad per second. Now the the capacitance of the sensor was, calculated as C equals to 2 pi epsilon naught ln of RB by RA. I'm going a bit fast because in the last class as well I have explained this question. So if you guys have any queries, like you can ask me after the solution. So this is the value. In this case, the problem with that is, with epsilon naught, that there will be a change in this value, right? So this will have a separate value. Let's say it's L1, and this will have a separate length L2. So epsilon will change accordingly. So what will happen? We'll have a epsilon of water, which will be with the L1 distance, and it will be epsilon of air, let's say air, into L2 distance. Now we know that L1 plus L2 is nothing but 1 meter. So by calculating this, we have got the, the value. What we have got was, just a second. By calculating this, we have got dc dt of nothing but 0.65 into 10 to the power minus 9. From this equation, we calculated dc dt equals to 80.22 into 10 to the power minus 12 into 80 minus 1 into dl1 by dt, change in the length of the water level. So we need to determine this value actually, dl1 by dt1. So it was the change in the water level, which will be nothing but the velocity of water rising, the velocity of the rising water. The values were determined to be this. So in the last class, up until this we have calculated. Now the subsequent question was, in that case, that what is the sensitivity and the offset of the previously mentioned sensor. So we have already solved this. The velocity of water rising was this. Now we need to know what is the sensitivity and the offset of the sensor. So which will be the correct answer? Let's take about a minute or so and try to solve it. Can anyone determine the value of the sensitivity? So what is sensitivity? What is the definition of sensitivity? Change in something by changing something. So what are those things? Let's take a minute. if you guys can solve it. Anyone? Anyone want to like try? What will be the answer? So let me give you a hint maybe. Yeah. So output and the speed of rise of water. Here, like they have already mentioned, the current is the output and the speed of rise of water is the stimulus. So how to calculate the sensitivity? Let me give you a hint. There was an equation that says that the current was nothing but V dc dt. As I have already told, that dv dt term will not be here because V is a DC voltage. So we know this term is our output and speed of rise of water here in this case. So that is the input stimulus rise of water, that is dl1 by dt, and we have our output here. Let's do one thing. Let me calculate this first maybe. So this was nothing but 80.22 into 10 to the power minus 12 into 79 into dl1 dt, right? This was the value, and we already know the value of dl1 dt. So how to calculate this? Change in current with respect to change in the speed of rise. Maybe I completed. So this is our input or the stimuli, and so what we'll do here, we'll get the output by input from this equation, and we'll just multiply this. So nothing but 80.22 into 10 to the power minus 12 multiplied with 79. So 6.33738 into 10 to the power minus 9 will be the sensitivity we require. So are there any problems? Yes. So here and here we found the value. Now we need to know the offset. What will be the offset? Without any input present, there should be an output. So the offset, to determine the offset, we need to put dl1 dt as 0. So if we put that 0, that is the output I will be 0 as well. So the offset value will be nothing but I0. So this is the correct answer. Okay. So we'll move towards today's class. So let me put that aside. Yeah. So there are like different types of thermal sensors. Uh, Broadly, we can classify them as the that contact based or the direct one, and there is another one that is non-contact based. So, what are the contact based and non-contact based thermal sensors? The first one here is the basic thermometer we have used from like old ages. So this is a thermometer. This is nothing but a digital thermometer. Previously, people used to like everybody has a thermometer that is called a liquid thermometer in their home. uh, which was like a manual one, a manual one. Right now, this is the digital one. It can be two types, but what it does, you put directly it in your mouth or underarms, and then after some time, it gives you the value of your body temperature, right? So what it does, it gives the value directly. If you put it near any skin like structure or something like that, it will measure your body temperature, and it will show that this is your body temperature, and you know the basic temperature of your body. And if it exceeds that, you know that you have a fever or something like that. So, but nowadays, after COVID specifically, this kind of a like thermal sensor is like very famous. What we do with it is like we directly put it I guess everybody has seen this. So you directly put it what is like point it directly towards your forehead, and it gives the measure of your temperature, body temperature, through IR. Sorry. Sorry. Let's move to this. Yeah. So what happens in this case, that it measures the values with IR range spectrum. Last day I have already explained that for thermal imaging purposes we use the NIR, MIR, and FIR ranges. That is the far infrared range, the mid infrared range, and the near infrared ranges. But in this case, they are using just the IR spectrum to determine your body temperature. So, I'm sorry, just a minute. Yeah. So it uses the IR spectrum. Now, so moving on to the chemical sensors, there are broadly speaking, we can divide it using two classification techniques. That there can be similarly using the previous technique, like there can be direct sensors, that is the direct chemical sensors, and there can be indirect chemical sensors as well. Other than that, the like we can broadly classify into two classes, where we can say that it is a physically reactive sensor, and there can be a chemically reactive sensor. So let's start with a chemically reactive sensor. So what happens in a chemically reactive sensor, that um, a sensor like this, in this there may be some active materials. The active material changes electrical response, or there can be a change of maybe resistance, or like a change in maybe inductance or capacitance. So by this change, by impedimetric sensing or something like that, we can determine the change in the chemical, because with change in the chemical, the material changes its electrical properties, not the physical one, only the electrical properties. And by changing like the resistance or the impedance, we can determine the change in the chemical. Other in other cases, like in case of physically reactive sensors, what happens? The material changes. There can be a shape change. So with and different kind of a thing, there may be a change in like this. So with this change in shape, we can determine that there is a specific chemical present in that. So what happens, that by the change in shape, we can determine which kind of a chemical is there. and after some time, after removing it from that chemical, it will revert back to the original state or something like that. So in these cases, like you can also see a visual representation of the like of the chemical, whichever chemical is near to your sensor and whichever is not. And other than that, there are like direct and indirect sensors. So in case of direct sensor, what happens that the stimuli is directly like captured by the sensor itself, and there is an electrical output. But in case of indirect type sensing, what happens that there is a stimuli, maybe a change in chemical or so, or maybe a change in gas or something. So the sensor gives as the output of maybe a optical change. What happens, like if you have a optical strip, and with change in glucose concentration, the strip may change color from yellow to darker yellow shades, or like or maybe a reddish kind of a shade or something like that. And to check if the sensor is working or not, we need an external circuitry to determine the electrical response, that is the electrical output. So these type of sensors are called the indirect type sensors. So now we can broadly classify these electrochemical sensors in mostly in like three parts. What happens in these three cases, that there is a change in potential in between these like two electrodes, then it is called as the potentiometric sensor. There can be change in the current, that is the amperometric sensor, obviously, like the change in the ampere value or something like that. There can be change in the conductance states, so it can be called like a conductometric sensor. So broadly classifying these sensors in three categories, that is the potentiometric, amperometric, and conductometric. So in case of like potentiometric, there is a change in electrical potential. Yes, and to remember the fact that let's complete the sentence and then we'll talk about it. Two electrodes, let's say. So we are determining the change in electrical potential between two electrodes, but specific thing to like remember, that is no current flow. So there shouldn't be any kind of a current flow, because without the current flow there is the electrical potential change in between two electrodes, and by this kind of a phenomena, the potentiometric sensor works. There was a technical glitch actually, so yeah. So anyone has solved it? Just wait a second. Let me open this. Yeah. So anyone has solved it? Or like if anybody is trying, then I will take like I will give more 2 3 minutes. Let's try for another 2 minutes, then maybe I'll discuss this. Yeah, just another minute maybe, if anybody is trying. So maybe I will just give a hint first. So in case of thermistor, we know RT is A R naught e to the power of BT, where RT is the resistance of thermistor at the temperature T, and then R naught is resistance of the same thermistor at ice point. Now maybe you'll be able to solve the question using this. So from the equations, from this one maybe, we can write that 1000 equals to a into r naught e to the power of b by 298, right? This is given in the equation. And from this one as well, we can write 465 equals to a into r naught e to the power b by 316. So by solving this one, we can just divide directly, and a are not term, that is that were the unknown terms, we can eliminate them. We can directly get that e to the power 298 by e to the power of b by 316. So from this we can determine the value of b, which is so the value of b is in this. So from this you can directly calculate the value of sensitivity. Now tell me the value of sensitivity then. We have got the value of b in this equation, right? We have got the value of b, we have got the value of rt already. So what will be the value of this? Sorry. Anybody trying to solve this? So with the sensitivity value, we'll just differentiate the primary equation, that is nothing but dRt by dt equals to minus a into r naught b by t square. This will be the last term, right? So from this we can write directly 1 by RT into TRT dt equals to minus B by T square. And the other parts we have to just directly calculate, that is equals to. So for this term we know already the value of B, right? Just wait a second, right? So this is the equation. So the term was into B by 290. Maybe I calculated wrong. Let's see. The value is 316.298. It's 2.88. By 465. The value is 41107. Yes, that's fine. So from this we'll get the value of sorry. So from this we'll get the value of 1 by RT into dRT dt. So what will be the value? So from this we can directly write My voice is not clear. Can you hear me right now? Hello?
Yes,
Maybe.
proceed, please.
Yeah. Okay. Fine. Yeah. So as we already know this value, and we already know this value as well, right? So we'll just divide those factors, and we'll get the value d by t square, right? And the value, or we have already calculated the value of b, and from this we'll get 4007.37 divided by t square, and we have also got the value of t, that is 316, that is 316 whole square. So 4007.37 divided by 316 whole square. So the value is 0.041, and this value is the value of the value of sensitivity here, or maybe you can write directly that minus 0.04 or something like that. This is the sensitivity. Okay, so move to the next question. Which of this is true and which of this is false? Which one is the true one? Which one is the false one? Just we talk about the first one first. Thermistors are inexpensive and rugged. What do you think about it? And then you may talk about this as well. So which one is true and which one is false? It is true that thermistors are inexpensive. That's fine. But do you think it's rugged? Is it rugged or not? What do you think? Or maybe we can move to this. What do you think about this as well? Can we use thermistors for remote measurements? So, yeah. Anybody likes to answer? Maybe you can type in the chat box as well. So thermistor is like it can't be used for remote measurements, so it's not possible. We have to learn about the like more in depth about the thermistor architecture to get to know if it like it may be rugged or it may not be rugged. But as we can't use it for like remote measurements, we definitely know this one is the false one. So we have to learn that this is the true one. It is obviously inexpensive in any of the cases, but in case of ruggedness, it may be rugged in your case, or it may not be rugged. But in this case, it's the true statement here. Yeah. So try to answer this question. Which of the following are true about thermistors and resistance temperature detectors (RTDs)? Which of the following is true for the thermistor and RTDs? Take maybe 1 or 2 minutes and then try to answer this. Yeah. So let me answer this question. The first one is obviously a true statement because thermistors are more accurate, obviously, and it may be cheaper than the RTDs as well. The second one is also true that thermistors have a faster response time than the RTDs. In this case, the third one is not true at all because it can temperature it can measure a temperature but within a limited range, and like RTDs has a huge range of operation, large range of operation, where like thermistors has a limited range but it has a faster response time. If your like application needs like a sensor which has a faster response time and you need to know the value very fast and you need the more accurate value, so you will need to use the thermistor. And the last sentence is also true because it's commonly made of ceramic or polymer materials. RTDs are made of pure metals, and due to this architectural problem, it has a lower response time as well. Let's try to answer this question. Which of the following is not correct? So first answer this question and then we'll talk about what are these things: absorption and adsorption. So please like try to answer these questions. Like if you don't know about the absorption and adsorption. Maybe we'll discuss this as well, but try to answer this. Option 3. It is exothermic in nature. Yeah. Okay. Others, what do you think about it? So maybe I'll explain this. So let's say it's an object when like first let us first explain the absorption rate. In case of absorption, what happens that if there are like particles moving from outside, what will happen that there will be particles here as well in the surface region, and there will be some particles within the object as well. So this is called as the absorption, right? And these are going to assist. And there can be a case where like, this is let's say absorption. What will happen in this case that there will be also moving particles from this, but what will happen that they will stay in the surface area, only in the surface area itself. So this is called as the adsorption and this is called as the absorption. So moving back to the question, adsorption is a surface phenomena. From this it's perfectly correct. There then adsorption is exothermic in nature. So why is it exothermic? What do you think? Sorry. Any idea? Why is it exothermic in nature? So what happens in this case is that this is like these surface particles are called as the adsorbent particles, right? When they like adsorb it to the surface of this particle, so what happens that energy of this adsorbent decreases actually. So there's like a production of heat as well due to the energy decrease of this adsorbent particles. There is a production of heat. So that's why it is an exothermic like process. The third one is that absorption is an exothermic process. So it's obviously not because the particles flow inside the inside the object as well. So it can't be an exothermic process. And absorption is a bulk phenomena. Yes, obviously, if a particle what do I say? If it penetrates the object wall, another particle will also do it, and it is obviously a bulk phenomena. We'll move to the next question. So let's try to answer this. Which of the following is true for chemical sensors? Which of the following is true for chemical sensors? In physically relative chemical sensors, reaction changes chemical property of the active material. So what we need to mainly focus on this case is chemical property of the active material is changed by the reaction. So is it a like physical chemical sensor or not? In case of chemical reactive sensors, what happens? That physical property of the active material changes, and in the next case, the sensing changes in optical strength when then gets converted into an electrical signal. This is an example of direct sensing. Is it a direct one?